Okay, so today's lecture we will start a new topic, which is diodes and rectifiers. In the previous chapters, when we discussed the motors, induction motor, induction generator, synchronous motor, synchronous generator, transformers, all of them were related to the power. And also there was a power system overview, power electronics overview. Then we didn't discuss a lot about electronics. So diodes and semiconductor materials, these are related to electronics. And they can be used in power as well in a topic called power electronics. So today's lecture, basically, we will go on overview. We will not go in deep details. We will go just a quick skim in some applications about the power electronics, especially in how we can do conversion between AC to DC, basically by using diodes. That's a small application. So diodes, in summary, it is one of the switching elements. One of the switching elements. What do I mean by switching elements? You can recall, go back to the recording and see power electronics overview. There is a pre-recorded lecture which is about power electronics overview. You can watch it so to understand the overall scenario. Then basically, in summary, or like a quick summary, the switching that we have in order to convert AC to DC or DC to AC or some like other waveforms, we need to have a switching elements. That switch, we don't mean the normal switch, which is on-off by yourself. We need to have a fast switching. Fast switching element means that the element that can be turned on or off maybe 1,000 or 100,000 times per second, which is, for example, 100 kilohertz, or 10 kilohertz as 10,000 switching time per second. And this, there is no way to do this using our hand. No matter what you are fast, you cannot do it manually. The only thing that you need to do, which is using software switching, or using electronic switching. Electronic switches are based on the semiconductor materials. And as we know, the semiconductor materials started its revolution since in 1960s, 1940s, something like that. Then we start seeing the computer from big size to be a smaller size because of the inventing of the transistor, which allows us to convert the vacuum tubes into a small transistor. Then after that, the revolution of the semiconductor materials makes the transistor from big size to be smaller, 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 until we see it nowadays in nano size. Therefore, we can see the computers right now in your cell phone, in your iPad, in your laptop. You can see it in small devices because of the semiconductor materials that makes that revolution. And we all know or aware that right now there is a challenging about the semiconductor materials manufactured. And there is, even like now, the government, they make a bill around, I think, 52 billion, something like that, for the semiconductor manufacturing to be inside the States, other than outside of the States, because most likely, as you know, that the vast majorities of the semiconductor materials are being designed or are being manufactured outside of the States. I think in Taiwan, South Korea, something like that. Then when we heard about the conflicts, like political conflicts, then we realized that, okay, or even like during the COVID pandemic, there was a challenging about the semiconductor materials. And you might be also heard about the designing of the new cars. There was a high demand, but not enough new car design that was during the COVID pandemic. And the reason because the lack of ICs, which is integrated chips. So these ICs, integrated chips, are basically the original equipment with it based on transistors, and these transistors based on semiconductor materials. So right now the trend by 2030 to reach a certain percentage of design or certain percentage of manufacturing inside the United States on electronics manufacturing. Then by 2035 or 2050, reach up to 90% or 80% of the demand. Okay, so anyway, the semiconductor materials makes the revolution in the electronics, in the computer system, communications, and the power system as well. So there are a lot of things related to it. In summary, again, like semiconductor materials can be used as a transistor, as an element which is switching elements. So we have switching elements like transistors, diodes, something we call it rectifiers, GTOs, etc. So transistors is a switching element that can be controlled. I send a signal, will be on, then send on signal, then turn off signal. So I can control it. And transistor, there are many types like BJT, IGBT, MOSFETs. We don't have enough time to cover it here. But there is other types of the switching elements. It's called diodes. Diodes is one of the switching elements, but the thing about the diodes, it's not like the transistor. It is, we cannot control it. So it's uncontrolled switching elements. So what does this mean? It will be turned on and turned off by its own, by itself. By looking at the waveform, it will be turned on and turned off. So by the nature of the waveform, the nature of the inputs. While the transistor, there is a gate signal that we can send it. Now I want you to turn on, I want you to turn off. So this makes diodes limited applications, not like the transistors, which has a most variety of applications. But the advantages of the diodes over the transistors, the diodes can handle higher voltages. And check the batteries. Okay, so the diodes can handle voltages higher than, more than the transistors, which is make it applicable sometimes in higher voltages. Some applications, we don't need actually to have a controlled switches. For example, when you convert AC to DC, you just, sometimes diodes is enough. Okay, so diodes material based on semiconductors. And semiconductors, as we know the materials, there's insulators, there's conductors, and there is some elements in the middle, which is semiconductors. As an example, like silicon or germanium. These one of the two. And I think there are some parts, these are rare elements, but these two are more found everywhere. So semiconductors, again, recall the valence. The valence has 4 electrons. You know this from, I think, chemistry. So if the valence has 7 electrons, 8 electrons, then most likely this is insulator, or also like 8 electrons. While if the valence has 1, 2, 3 electrons, this is conducting materials. While when it is valence has 4 electrons, this means this material is neither conductor or neither insulator. So this will be in the middle, which is, we call it semiconductor materials. And again, we are using this in electronics. So the vast majority of the electronics, all of them based on silicon and germanium. So but silicon is more common than germanium because of the availability of the silicon. So the diodes allow us, or allow the charge to flow in one direction. This means the current will flow in one direction. And it will block the current from going in the other direction. Basically, it's a unidirectional element. This is how the diode look like in real life. You will see this. This means this is the cathode. This is the anode. Or in other words, this is the positive, this is the negative. So the diodes allow the current to flow in this direction. This is the current can flow in this way. However, if there is a current flowing in the opposite way, it will block it. Okay? It will block the current from the other direction. So it will allow the current again to flow in one direction. So how can we make the symbol for the diode? So since the current, for example, in this scenario, going to the right, we will make it as an rectangular here. So I'm sorry, triangle. Triangle, it runs towards the right. This means the current can flow this way. That's the first thing. Then the other thing, which is the current will be blocked in the other direction. So we're going to put like this way. So if anything go in the other direction, it will block. If the current go this way, it will go with the other. So as a result, we make the symbol of the diode like this way. That's the symbol of the diode, which is that's what we see here. So the current will flow here from anode to cathode, or from positive to negative, while it cannot flow from negative to positive. That's the diode, which is basically, this is the characteristic of the diode, and it's uncontrolled. I cannot say when will it be open, when will it be off. The only thing that I can do, which is the inputs. If I have a way to control the inputs to the diode, then, or change the diode position, then I can handle it. Okay, the ideal diode operation. Basically, we will assume it is an ideal diode. What's the difference between ideal diode and practical diode? The diodes has, since there is a silicon material, has its own resistance. A small resistance will cause a small voltage drop. If it is from germanium, it will cause another small voltage drop. Basically, silicon will causes around 0.7 volts voltage drop, while germanium will cause around 0.4 volts voltage drop. When we assume ideal, we will not consider this. We will not consider the voltage drop, 0.7 or 0.4. But here, this is for your information. So for this course, it's just one lecture about the diodes and rectifiers, so we will go for fast about it. So we will assume every time it is ideal. So don't worry about the voltage drop, 0.7 voltage drop in silicon or germanium. We will assume everything zero, no voltage drop. It's ideal diodes. Okay? So the model, when it is the VD, the voltage applied positive, it will allow the current to flow in one direction, which means it will be replaced by short circuits if the current going this way. It will be short circuits. While if the current going in the opposite way, the model of it will be open circuits. Okay? So you need to be consistent in how to do or to draw the equivalent circuit for each one. Okay, does this make sense? So keep in mind, look at the current directions or the voltage polarities. The positive must be at the anode, negative at the cathode, then or the current going from anode to cathode. Let me write some scenarios or some circuits to see how we can handle it. So I'm going to assume some DC circuit analysis, like I'm going to write this example. We have here 10 volts, 3 ohms. Here is a diode, and 6 ohms. Okay. Now, how can we solve this circuit since we have a diode? Remember, the diode here will allow the current to flow in one direction. So basically, when you used to see these kind of questions, we used to assume the current direction. So the current will go out from the positive of the source, right? So the current will go out. Here is I. Then I'm going to call it as IS. Then it will be split it. So it will be I1, I2, right? So look at I1. The current will go here. The currents will be blocked at the diode, or will the diode allow it? What do you think? The current will be blocked or not? No, it will not. So what should I do? Redraw the circuits by replacing the diode by short circuits. The diode now it is short circuits. Here is 6 ohms. Then here is another 6 ohms. And my target is to calculate the current IS. So how to calculate the currents? Just find Z equivalents, then it will be V over Z equivalents. So IS will be V source over Z equivalents, which is R equivalent here because it's DC. Whatever. which is going to be 10 divided by 3 plus 6 parallel with 6, which is 6 parallel with 6, 10 over 3 plus 3, 6, 10 over 6. So I will be 10 over 6, which is 5 over 3 amperes. Okay? That's simple. Another example. I'm going to assume the same scenario, 10 volts, 3 ohms. So I'm going to make the diode in the opposite direction. Okay. So in this scenario, as we know, the current here will be IS, then it will be split. It will be I1, I2. Now, do you think I1 will flow in the diode? No, because it's in the opposite direction. So what we need to do is to replace the diode by open circuits. Plus minus 10 volts, 3 ohms. The diode now is open circuits. 6 ohms, 6 ohms. Now, since it's open circuit, the 6 ohms resistor can be removed, right? Because the current is 0, Ohm's law, V times R, Ohm's law, V equal I times R. I is 0 times R, which is any number times 0 will be 0. So the voltage and the current both will be 0. So as a result, this yields to be 3 ohms, 6 ohms. And here's 10 volts. Okay? How to find the currents? I will be V over Z equivalence, which is V over R equivalent, which is 10 divided by 3 plus 6, which is 9. 10 over 9 amperes. Okay, does this make sense? So you need to be aware how to deal with the circuits. Now another scenario. Ohms, 10 volts. Okay, we need to calculate the currents. Oh yes, but I'm going to make 2 conditions. First condition, or two cases. Case A, this is V source. When V source equal 10 volts, case B, when V source equal to negative 10 volts. Okay, what should I do? Look at this circuit. Then let's assume case A, scenario A. When V source equals 10 volts, the current I source will go out from the positive, right? So what will happen? V source, then the current will go out from the positive, 2 ohms, then it will flow in the diodes, which will make it short circuits. What will happen to the other diode? Since the current flowing here, the diode will block it, so it will be open circuit. Okay? Does this make sense? So here is 10 volts. Then we can say I will be V over R equivalent, which is R equivalent here 2 ohms, because the 4 ohms is open circuit, it can be removed. So this will make it 10 over 2, then it will be 5 amperes. That's scenario A. Scenario B, when V source equal to negative 10 volts. When it is negative 10 volts, this means IS will flow in the opposite direction. If it is negative, this means it's here is positive, negative. Then IS will flow here in the opposite direction. That's what does negative mean. So the circuits will look like this. Here's negative, positive, 10 volts. Then IS is flowing here. Here is 2 ohms resistor. Then this diode will be blocked because the current going this way. Going up, it will be blocked by the first diode. The second diode, it will be short circuit because the current flowing here. So as a result, to find IS will be Vs over R equivalent, which is going to be here 10 divided by 4 plus 2. So it will be 10 divided by 6 amperes. This is IS. Okay? Keep in mind, I assumed IS going this way. If I assume IS going in the other direction, it will be negative sign. Okay, does this make sense? Any question? So that's basically how we deal with the diodes circuits when we deal with DC circuit analysis. In AC, there will be some differences. But for these kind of circuits, most likely it will be based on DC, while in AC, we will discuss it now. There is an applications, or some applications in electronics, those called rectifiers. So the word rectifier is important. What does rectifier mean? This means converting AC to DC. This is one of the most common applications on rectifiers. As we know, the utility outlet here, the wall outlet is 120 volts RMS, which is based on AC. Your laptop charger, DC, 15 volts, as an example, or 19 volts, whatever. So we need to convert AC to DC. Basically, you are using the charger, or even like the cell phone is DC, there's a battery, wherever there is a battery, it's DC. The charger actually converting AC to DC and doing some controls on the voltages as well. So we need to convert AC to DC by using a rectifier. So the rectifiers, you can find it everywhere in the most of chargers. So basically to convert AC to DC. Then after that, when we convert AC to DC, there is another part of control to make it with the same voltage level, which is 5 volts, etc. Now in rectifiers, again converting AC to DC, those are based or relied on the diodes. So the rectifiers here, we will discuss in today's lecture 4 types of rectifiers. The first one is called half-wave rectifier. This is number 1. So half-wave rectifier circuit looks like this. So you need to either memorize this circuit or write this in your note sheets, okay? Because it's very important. Then when you look at this circuit, then you know this is a half-wave rectifier. You are required to either memorize or write this in your note sheets. All of the 4 types of rectifiers. This is number 1, which is half-wave rectifier. So as an example, this is a source. Then we have a diode in series. Then we have a resistor. Our target is the source that we have is AC. Then the load is DC. We need to convert AC to DC. So let's assume the load is your cell phone or your laptop. Then the VS is the wall outlet. So by using single diodes, can we convert AC to DC? Let's see. We will assume the AC is 10 sine omega t, 10 volts sine omega t. This is how the waveform of the source will be. So you can notice that there is a positive, negative, positive, negative. So the diode allows the positive to pass. Diode allows the positive side to pass and block the negative. That's what's happening. Okay, so whenever Vs is positive, this is scenario A. Whenever Vs is negative, this is scenario B. So when it is positive, this is scenario A. The diode will be replaced by short circuits when it is positive. When it is negative, scenario B, the diode will be replaced by open circuits. So we will see that when it is by open circuit, it will be 0. When it is by short circuit, it will be the same. It will be flow. So let me draw the waveform for everyone. So here is Vs of t. Then here we have Vr of t. Vs is the source, Vr is the load, and also I would like to draw the currents, I of t. So the source, it is sine wave, so it will be like this. standard mode. So when we have this kind of waveform, I prefer to make a guidelines at the intersection of the t-axis. So the intersection of the t-axis here, 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 here. Then try to split it. So the first part is positive, second part negative, positive, negative. So since we have a half-wave rectifier, it will allow the current to flow only at the positive side. So at the positive side, this will make it positive. At the negative side, it will be blocked. Positive side will pass, negative side will block. And don't forget to write the values. Okay, so the values here when it is at the negative, here is bounded between negative 10 to 10. Then here are the diodes or rectifiers. This is at 10 volts. Okay? So the sign between negative 10 to 10, and here the peak is 10. So you can say, look at Vs and Vr, only the positive part will pass, while the negative part will be blocked. This is because of the diodes. Then what will happen to the currents? The current is actually Vr of t over R. R here equal, let's assume it 2 ohms. So it will be Vr of t over 2. Then the waveform will be exactly the same as the voltage, but with different magnitudes. So it will be pass at the positive, and then here will be 0. But the magnitudes here will be 10 over 2, which will make it 5 amperes, the amplitude. So when you draw this either in quizzes or exams, don't forget to write the axis, t. Don't forget to write Vr of t, Vs of t, I of t. And don't forget to write what's the value of the maximum value. Here it's 5 amperes, 10 volts, then the first one between negative 10 to 10. Okay? Is this clear? Now, remember, this is a rectifier, half-wave rectifier, converting AC to DC. Now look at VR and I of t. Are those really DC? No, they are not DC. So this rectifier has a poor performance, which is not exactly DC. Yes, we don't have a negative, but we still have this situation. So what should I do in order to handle this? We will add a capacitor in parallel. This thing, which is second type, is called half-wave rectifier with capacitor. What's the point of adding the capacitor? The capacitor will charge, discharge for a specific period of time. So this allows us to take some time. So whenever we have Vs larger than 0, this allows the capacitor to be charged. Then when Vs less than 0, it will not go direct to 0. It will allow the capacitor to be discharged. Then it will go to 0. So what's happening? I can redraw the waveform so you can see the difference. Here is the guidelines. Then here this is bounded between 10 volts as an example, negative 10 volts. So this is Vs of t, now Vr of t, but keep in mind here with capacitor. Then here I of t. Okay, so the positive will be the same, but the thing which is the capacitor will allow us to charge and discharge. So the other guidelines that we need to add is at the peak of the positive side. So what's happening? The VR will follow the waveform. Let's go at the positive cycle. We'll follow the waveform. So it will follow the waveform, okay, until reaching to the top. Then it will not go decay with the waveform. It will be slower because the capacitor has more charge. than what we have. So the capacitor will allow going from the top to the zero in a in slower way. It will slow down. So we'll slow down, slow down, slow down. Then here we'll go back to positive, then slow down. Okay, slow down, slow down. Come on. Then go back, slow down, and so on. So that's the waveform look like, and the peak of it is 10 volts. How about the currents? The current will be the same waveform, but different peak, of course, because you can apply Ohm's law. So here is the peak around, we'll say 10 over 2 will be 5 amperes, because R is equal to 2. So when you look at this graph, you will realize that the waveform is, it's better. Is it DC? Not really, but it's better than the first one, right? Is this correct? So what should I do to make it, to improve it? We have another application, a third application. See, so here I'm trying to show you how the progress of inventing the rectifier. First one, we did it, and it was like positive. Then we did with the capacitor. It will make it better. Now we need to improve it more. So the challenge that we have in the rectifier, which is this part, the negative part, will be 0. Okay, this is something that we don't like. Is there a way to use this one, but not making it 0? And we don't want to cause a lot of losses because this one will be 0 or something like that. Yes, by trying to find the absolute value of the waveform, right? So by trying to find the absolute value, which is something that we create, this is the third application, which is full wave rectifier. Full wave rectifier, it's based on 4 diodes. This is called D1, D2, D3, D4. So what's happening when V source larger than 0, D1 and D2 are short circuits, D1 and D3 short circuit, actually the odd are short circuit, and the even D2 and D4 are open circuits. How about when Vs negative? It will be the opposite way. D2 and D4 are short circuits, while D1 and D3 are open circuits. This is the rule. So this is allow us every time VR will be positive. How we can do this? Let's look at this scenario. So again, the first scenario, here D1 and D3, when Vs larger than 0, D1, D3 short circuits. D1 and D3 short circuit, this means the top, this is short circuit, this is short circuit. So what will happen? The current will flow from positive, then it will go to the positive part. Then return the negative, go back to the negative. This yields VR equal to Vs of t when Vs larger than 0. The second scenario, when Vs less than 0, this allows the current to flow in the opposite direction. So the currents here, we have D2 and D4 are short circuits. Then the current will flow in the opposite direction. So the negative will be at the positive. Then the positive will be at the negative, which means flipping the sign of the voltage. As a result, VR will equal to negative Vs of t, such that when Vs less than 0. As a result, we realize VR of t, it can be either Vs or negative Vs when Vs larger than 0, or negative Vs when Vs less than 0. Then as a result, VR of t equal to the absolute value of Vs of t. That's the way, or that's the thing of using the full wave rectifier. So what will happen if we need to plot the waveforms with and without capacitor? Let me draw it, I think, here. I can draw it here. This is Vs of t, Vr of t, then I of t. Here without capacitor. Which is still application number 3 without capacitor. So Vr, Vs of t, like this, between plus 10 volts, negative 10 volts. So what will happen when we have full wave rectifier? It will be the absolute value. So this will make it positive, 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 positive. And the amplitude is 10 volts. What will happen to the currents? Will be the same as the voltage, but will be 10 over 2, which will make it 5 amperes. Okay? Now this waveform is better than the first application because the negative parts will no longer be 0. But is this really DC? Not really. So what should I do? We make the 4th application by adding the capacitor. So which is step number 4, by adding capacitor. So basically, it will be the same circuits as that one, but we will add capacitor. Okay? So the capacitor will allow us to charge and discharge in a similar way that we discussed in the half-wave rectifier. It will be very similar way here. So now I will draw the circuit again. Again, I know I'm going fast, but you can go back to the recording, or I already uploaded this. You can send you this PDF file, so you can have access to it. So anyway, let's try to finish so we can have enough time for the quiz. So we have Vs of t, Vr of t, I of t. Okay. Here is the waveform for Vs. Then again, locate the critical points, which is the intersection at t-axis and at the peaks. So what will happen is it will go like this way. Then for the discharge, it will be slower. Then it will charge, discharge, charge, discharge, charge, discharge, charge, discharge. Then the same thing for the currents. Charge, discharge, charge, discharge, charge, discharge, charge, discharge. So if the magnitude here between 10 volts, negative 10 volts, then here 10 volts, here 10 divided by 2, which is 5 amperes, as an example. And all of this t-axis. Then when you look at it, is it DC? Kind of. But when you increase the large of the capacitor and make the capacitor slower down, then the waveform will be better. So if you use a better performance capacitor, it will be like this. So you can barely see these things. So here, with good capacitor value. Then this will make it DC, and that's most likely with the original rectifier that we have based on full wave rectifiers. That's what we use in the applications, based on DC. Okay, so other diode circuits, this we didn't have enough time to cover it, so forget about it. Any question? Okay, so let's end the lecture and start the quiz.